Hello, my name is Jacob Coffing. I'm the senior engineer here at Purdue NMAC. Today we're going to talk about a project we're working on with IoT and machine sensing. This project is in collaboration with a few other students here at Purdue, as well as senior research scientists of Burke Nanotechnology Center, Nithin Raghunathan and Harris Musalas, as well as PhD candidate Unsub Kim, who is working as an intern here this summer at NMAC, and Ilki Akturk, who is a PhD student in chemical engineering as well. So this is a setup to help manufacturers gain more data from their machine, for instances and predictive maintenance, as well as process anomalies. So how we set up a machine tool is we use readily available IoT sensors. So yes, we use some research, some sensors that are being developed by Burke, but also there's a lot of widely available and economically suitable IoT sensors. So once we establish which sensors we're going to use on a specific tool, we then deploy them on the manufacturing equipment, which this can be legacy equipment or state-of-the-art new equipment. Today, mainly, we'll be discussing subtractive manufacturing processes, but this can be used on robotics, injection molding, stamping. This can be taken to any mechanical application. So once we've deployed sensors on the given piece of manufacturing equipment, we begin to gather sensor data, controller data, the product inspection reports from quality control, as well as the operator log sheet. So if a tool breaks, if they have a non-conforming part, they digitally log that, then we can take that information and overlap it with the machine data as well as the process parameters. What task was the machine performing when this given error or issue arose?
Sorry. Thank you, Jacob, for introducing me. In this slide, I want to explain a little bit about detail of the architecture of our framework, how to we develop our system, and how we collect the data, and so on, from machine and sensor, and even sometimes operational log or maintenance log. We collect all the data to the data acquisition system. We are using MT-Connect framework. MT-Connect is a kind of middleware which can make a connection between sensor data or machine data to the software. So by collecting all the data, we collect all the data goes to the database. And first of all, we show the data, real-time data and integrated data as using the visualization tool like a Grafana interface. And using the collected data, we build and develop some model to predict something. Model can be sometimes analytical or equation-based model, and sometimes we are using the artificial intelligence technique like machine learning or deep learning. Based on the analysis scenario, like someone may have interested in the productivity or anomaly detection or sometimes machine health. The result from this model goes to the visualization tool. So finally, the end user can see the difference of the machine data or history of the data, and also see the result of the machine learning model.
So this is some different types of sensors that we're currently using here in the test bed. We have the wireless vibration sensors, which are from company Best, who we're currently doing a partnership with, as well as IFM sensor. That's mainly the sensors being used on this piece of equipment currently, as well as a higher end PCD sensor and NIDAC.
And I want to introduce a little bit about my acoustic sensor. This is an example of my acoustic sensor. I'm using a stethoscope. It is a really real stethoscope. And like my concept is that like a doctor examines patient by listening to the sound from the patient. I attach the microphone. This is the USB microphone. I attach the microphone at the end of the stethoscope. I listen to the sound from the machine. So if I know the normal sound, normal condition of the sound from the machine, I can tell that anomaly rate or anomaly result to the end user. It is my concept. You can see the sensors. Yeah.
So do the machines talk?
Huh? Yeah.
Sometimes.
Yeah. Sometimes. Yeah. Yeah. Thank you. And we can also use the other type of sensor like temperature or vision or power meter. And as I said, we are using empty connect to communicate a machine or legacy machine or sensors. And we have some example of affordable edge device computers like Arduino, Raspberry Pi, or headless computer. So my point is that sensor, middleware, or edge computers can be differed by demand. We can customize everything.
So these are some examples of different deployments around the community. Currently, you're standing in the Intelligent Manufacturing Testbed. With the equipment here, this is where we develop all of our methodology as well as trying different sensors and finding out what works. When we started this project, we had something like 80 sensors we started with, and now we're down to 3 or 4 different types of sensors. So it's been a journey getting here.
Yes, so we deployed our sensors and our system to local company, and also we deployed the sensor to the Berk nanotechnology sensor facility room to monitor the vacuum pump, whether it is the condition of the vacuum pump is good or not. We can tell the difference of the sound signal if we detect it. And we deployed some sensors on the local company, as I said. This is the map of the Purdue, around Purdue. You can see some companies logo in here. And we deployed the sensor on in standard industrial case, we deployed the sensor on the 3-axis milling machine and also legacy pipe bending machine. For example, in legacy pipe bending machine, there is no way to communicate with the machine controller because it is a legacy machine. So I put my sound sensor and other sensors. By listening the sound from the machine, my model can tell you that whether which part were made, like by comparing the sound difference and how many parts were made, like that. And this is the example of the voice IPN. I put the sound sensor on the pipe cutting machine. In this application, my model can predict how many parts were made and also how many tools were used. And this is the Biotown case. I put the microphone in the middle of the powerhouse. There are 6 power generators in the powerhouse. And I developed some model to figure out which power generator is running. And this is,
So this here is C&D technology. So we've deployed the acoustic sensors on a lead molding machine. So some of the issues they were having is it's a lead molding machine, so it's it's a dirty, harsh environment. So there was an issue of lead oversplash. So the lead oversplash would get to hoses on the pump, things like that. It would cause a leak. Well, it's a very large unit. Within minutes, hundreds of gallons of hydraulic fluid covered the floor. So they were down, loss of thousands of dollars in hydraulic fluid downtime, lost production, as well as maintenance time to keep up with it. So we've deployed an acoustic sensor to monitor the pump, the health of the pump for one, but also a simple sensor. It was like a $500 investment for the tank. So we've tied it in with their PLC where when that tank drops over 2 inches within 30 seconds, it kills the PLC and kills the machine. So instead of cleaning up 100 gallons, 200 gallons of fluids, it might be 2 or 3 gallons of fluids. So, a lot of companies get scared when you go in talking about IoT and predictive maintenance and things of that nature. It doesn't have to be a large project. You can start small. Some of the things we're trying to do is give web-based dashboards to these companies. A lot of companies, at the production level, the supervisors don't know what's happening on the shop floor. They have to go down there and figure it out. With this, it's readily available. They can pull up their whole shop floor and look at the status of every machine on the floor, what parts are being run, how many of them have been run, what's the status of the machine, is it down, is there a maintenance issue? But also we can predict availability. Maybe they have more availability on machine A versus B. Performance of that machine, they may have quoted the machine for a certain rate and it's not meeting it or it's exceeding it. Then also quality, the quality of the part. Based on this historical data, we can detect how good of a product is being manufactured. One of the big things also is the predictive maintenance. So a lot of companies run in what I call the fire stage of maintenance. They run until something breaks. Then it's all hands on deck, they're ordering parts, the machines are down, and it can be weeks to get a tech in, it can be months to get parts in some cases. What a lot of companies try to do is we're going to do preventative maintenance. We're going to do this maintenance on this machine every 2 months, every 3 months. Well, production schedules come along and they get behind. Almost every company I've worked for that has implemented PMs, they kind of get put on the back burner, which in return they run the firehouse method. So what our plan is if we know what a healthy process of that machine looks like, that based on historical data that from operator logs, things like that, we can start to extract features and set alarms and parameters to where that the machine, maybe this bearing is going to go out in the next month. You can have product on order, techs ready to come in, but also you can transfer that production to another line. So here are some examples of different web-based dashboards. This one is actually the machine right here, where you can tell machine availability, what status it's in, the programs being run, the current tool, the spindle loads, the overrides. So operators can't increase or decrease the overrides based on competition of other shifts and things like that to try and get more parts out, and it keeps a more flatlined system. This is standard industrial, their production log. This is one of the pipe bending machines, as well as Biotown Ag. So this is the machine setting right here. So this is basically our setup. We have power meters on the machine, we have acoustic sensors, as well as some very low cost MEMS sensors. It's a Herco 3-axis machine that we're using IFM vibration sensors on currently. So we have vibration sensors on every axis motor. So a CNC machine runs on a ball screw. A motor runs that ball screw. So we have these vibration sensors on every motor, as well as the idle bearing side. So you have a drive side and an idle bearing side. So we're currently monitoring both sides of this to try and get the most out of the monitoring system, which it's all running through a panel PC right there.
From sensor data and the machine data also goes to MT Connect agent server. The server data goes to the MySQL database. And using the Graphene interface, we build a web-based dashboard, so you can access the dashboard whenever you want and wherever you are in. So this is the example of the dashboard of this 3-axis milling machine. So you can see every information from this dashboard in a real time. And you can see the history of the machine availability, and also you can see the history of the controller mode and execution mode. All this information is from the machine controller. And I'm going to show you some example of the sensor data. These are the spindle speed log of from the machine, and spindle load, and feed rate, and axis load. We can see this is the warm-up cycle of the data, and we can see the power consumption, how many power was consumed, and this is the sound sensor data, and this is the MEMS sensor data, and you can see the accelerometer vibration sensor data on each axis motor and spindle. You can figure out which motor is attached from the spindle and axis, and you can see the velocity and displacement and velocity peak and acceleration crest. These are the example of the I/O link, which is placed on the idle bearing part. You can see every information from the accelerometer, and also this sensor has capability of the measuring temperature. In this part, I want to explain a little bit about the machine learning procedure. So from the various machines or some part, component, we attach all the IoT sensors, right? And we collect all the data. This is the example of the raw data. By extracting some features from the data, we build this kind of neural network. And we are using mainly using the classification method. The end output is the result of the model. Output can be anything. Like it can be machine health, and it can be productivity, or other things. So this is the procedure of how we build the model for the AI. This is the detail of the example of using the sensor and the AI. As I said, we attached our sound sensors and internal stethoscope onto the machine. This is a Haas milling machine, 3-axis Haas milling machine. So, yeah.
So this was an example we were trying to showcase was a new tool versus a worn tool. So in subtractive manufacturing, the tooling is a big part of it. You know, if a tool gets worn, the part can go from a quality part to an out-of-spec part. So in this example, we're using our old VF2 Super Speed. We're using a 1/2-inch end mill. This is the part number, and the comparison, like I said, is new tool versus old tool. So basically, we have a tool here that has a edge break on it. So a lot of companies buy a sharp corner end mill. Well, the edge chips off a little bit, and a lot of times they're still used. So the cutting parameters from the new and old were 12,000 RPMs, 0.8 depth of cut, 75 thou step over at 500 inches a minute. So here are some results of the acoustic sensor. So by the naked eye, it's very hard to tell, you know, which was the new tool versus the worn tool. But Unsub will talk more about that here in a minute. But we also have, not in this slide, but the vibration data. So the vibration data from the new tool, from the new tool to the old tool was almost 1.5 times the vibration with the worn tool. And this is a tool that probably a novice operator wouldn't have noticed and would have continued running, but the results speak for itself. It's almost 4 or 5 times higher surface finish with the worn tool versus the new tool.
And so in this graph, this is the a time domain raw data of the sound signal. You can see that you can figure out which is the idle or which is cutting easily. But if we compare between new tool and worn tool, it is really hard to figure out what is the new tool or the tool condition. And this is the frequency domain result. The color means the intensity of the signal. The y-axis means frequency domain. And so, from here, you can see the cutting, you can tell the cutting, but it's really hard to figure out which one is the new or worn tool. And so we are introducing the automatic speech recognition technique, which is used by Siri in Apple and Hey Google in Google. And so by using this technique, it is mimicking the human hearing in a frequency domain. So this is the example of the, it is called by Mes spectrum. So I extract the feature from the raw data as a Mes features to see the difference between the signal of the according to the condition. So this is some brief of the my machine learning model. I'm using artificial neural network from the Mes spectrum features. I trained all the data between new tool and worn tool, and my model output can be new tool or worn tool. My model can determine which one is you are using. So I trained all the data, and
So to Unsub's point, a lot of times I get made fun of here because I'm more of an industry person than the research side of things. So we'll be in a meeting and the machines will make a sound and I jump up and take off running and they all laugh like, what's going on? So basically what he's trying to do is get the machine to do that for itself, to know, hey, this tool's broke, we need to stop. Without having an experienced person there to understand what's going on. So based on the model, the very complex model that he's done, he's able to tell with 95% accuracy on sensor 1 and 99% accuracy on sensor 2. He can identify new tool versus worn tool within a 99% accuracy. Looking at that graph, one could never tell, but with this deep learning model, he's able to do that. Our next steps is to create an HMI or a operator interface. So now that we are getting all this data is great, but data is useless without actual parameters. So our next step is to create an interface where the operator can, at 245 tool broke. Then we can go back, extract that data point just before it and start to build detection models that will allow the operator to know when before a tool breaks, that it's breaking. And it can also be used as a training tool for some new operators that might understand the sounds and the vibrations in the feel of the machine. Then when you have a monitor in front of you telling you, hey, there's an issue, then you start to pick up and learn these type of things.
My name is Alexander Meredith. I'm a graduate research assistant here at the Indiana Manufacturing Institute. My lab is the Digital Enterprise Center, and I'm 2 months into my master's program. Today I'll be presenting 2 research projects that the DEC lab has been working on. One is the model-based work instructions, leveraging the HoloLens 1. It's an augmented reality device. And the second project is called Assembly Digital Thread. It's using a machine vision model in conjunction with smart tools for fastener detection, as well as foreign object detection, fastener assembly, as well as other features that work into a digital twin model. The main purpose for all these technologies is for the digitization of manufacturing processes. The United States is in Industry 4.0 right now, which is considered the 4th industrial revolution. I'm sure everybody's familiar and aware with that. And so the main purposes for leveraging digitization of our manufacturing processes is so we can have increased connectivity, leverage artificial intelligence through the forms of sensors as well as machine models, and gathering analytics that we can use to make informed decisions about machinery and about our processes. These are all for different types of interfaces, whether they're human-to-human interfaces, human-to-machine, machine-to-machine, and they are also for the purposes of increasing productivity, reducing errors, reducing failure rates. So model-based definition as an overview is taking digital product definitions and to eliminate error-prone information exchange. So previous information exchange in manufacturing practices was static. It was paper drawings, it was communication amongst engineering professionals. Those systems are antiquated and they were prone to errors due to either things as simple as handwriting mistakes, reading mistakes, or other things of that sort. Model-based definition leverages not only product data information that's contained in models, whether it's a 3D model, whether it's a spreadsheet type of model, or things of that sort, and it allows manufacturers to make more informed decisions. Model-based definition comes in a variety of factors. Some of those factors include things such as 3D PDFs. So it's a PDF document that contains an interactive 3D CAD file, or it could come in the form of augmented reality as we've developed. So the first section, and we'll have a demonstration afterwards, after the presentation, if anybody would like to try on the HoloLens themselves to take a look at it, is augmented reality MBWI. It's part of model-based manufacturing. So this is for assemblies, this is for processes for operating machinery, and it is one of the first stages, if not the first, for product life cycles. To go over as an overview of what the project's for, it's for developing frameworks for the generation, creation, distribution, and revision of work instructions. So work instructions are simply instructions that are developed for operators so that they can do a process and they can do it effectively. As I spoke about earlier, the model-based work instructions are to substitute paper and static work instructions, and they're interactive for digital assemblance. Finally, the point of use information is very critical. Model-based work instructions have information for the operator at the point of use. In comparison to an operator referencing a computer on the side of their workbench or referencing a paper document, they have information about the product, about the assembly right at the point of use, which is very important because it eliminates errors. It allows increased productivity for an operator. And you can tie live information into the IoT structure that is established at a company, because you can have informed analytics. Basically, an operator can instantaneously say, hey, I have an error here, and an expert, a subject matter expert, can be called in remotely and leverage the camera that's on the HoloLens and have a live feed and guide an operator through an error that might be occurring with an assembly. Additionally, you can have instances where there is maybe a change where there's a part that's missing from the operator's workbench, right? Then a supplier within the company can say, okay, here's an informed decision. This is a potential alternate part, or this is a part where we're going to have to suspend assembly until we get a replacement for that. So as I spoke about earlier as well, there's two forms, 3D PDFs. 3D PDFs, like I said, have a three-dimensional model available. There's a video here that shows you what a 3D PDF looks like. They're great for the purposes of transmitting information quickly, but they don't have the same benefits of point of use information as the HoloLens does, because the HoloLens, again, the operator can see their real workbench and their digital workbench in real time. This is going to be the video demonstration that'll show preemptively to what we've developed, and then further after the presentation, anybody that's interested in putting the HoloLens on themselves can take a look. So we have our app interface. So we have a HoloLens, and as you can see, in live time you can see a digital environment for the workbench. There is digital bins that coordinate with the physical bins. There are digital components and parts that are being placed inside of the physical assembly. So in this case, we have a black part body for a water pump, and we have the digital pins being placed in the correct locations. Those locations are to guide the operator for the physical parts that are in their bins. There is the interface for the HoloLens. We have a Bluetooth keyboard. The keyboard is used to advance the steps for the operator, and the QR code is on the workbench. That QR code has the same distance in physical space to the workbench as the digital QR code has in the virtual workspace. So that's how we can coordinate and overlap the digital work bins for the physical work bins. There's also a bill of materials, so it shows the operator what materials should be at their workbench. And there's also, if you can see on the left-hand side of the screen, a assembly drawing. The assembly drawing is more so for legacy operators, so operators that are accustomed to paperwork instructions and drawings. It's there as another benefit. Our lab is going to be developing a more advanced model on the HoloLens 2, which is the second HoloLens device from Microsoft. That device offers a lot more usability. There's digital buttons that you can press, so somebody could be wearing the HoloLens, and to their right they've got buttons where they can swipe through different videos, different scenarios for different steps. There can be different chapters, for example, of an assembly, or different work process levels. Additionally, it has real, actual distance tracking with the form of multiple cameras. So it gives you a true detection, and there is also true hand detection, which offers a lot of implication for things such as foreign object detection or actual worker safety, etc. So the assembly digital thread is the project behind me, on the workbench behind me. It's part of model-based quality. Model-based quality is leveraging the model, the 3D model, which is the point of reference, the point of truth, in the digital twin for creating a quality process to ensure accuracy in dimensions and tolerancing, etc. So the project overview is that it's a system that was developed so that you could have an aid that monitors assembly processes for fasteners. So making sure fasteners are correctly torqued, that they're not over torqued or under torqued, to make sure that fasteners are assembled in the correct order, to make sure the correct type of fastener is used, because there's assemblies where there's multiple types of fasteners used at the same time, as well as foreign object detection. This is very important, and I'll show you in a live demonstration during this presentation. To show how the current data flow operates, there's a graphic here, and we have a digital tool. That digital tool is connected to our computer and our program via Bluetooth. That captures the torque value that it just was given by the operator, and it sends it to the program. And the program checks to make sure that value was accurate, as well as to make sure that the tool was in the correct location. We have the desire to expand on our progress by feeding into an MES system, a manufacturing execution system. There's different products. For example, Solumina, made by iBase-T, is something that's going to be linked to the INMAC IMI Testbed here. And in fact, I've been going through training with Solumina all this week, so a lot of hours behind the desk. The MES system is really beneficial because it captures things such as consumables, such as fasteners, right? Checking an ERP system. It also shows the correct work order instructions in conjunction, and it also proves quality. There's an actual data point for when a fastener was torqued, how far it was torqued, and it can be checked back to the digital twin, which is the reference model. We trained a machine vision model using a plethora of images to show different types of fasteners. So in teaching the machine vision model, it shows you what type of fastener it is, the coordinates of the fastener, and the detection level. In other words, how accurate it thinks it is. To show, to summarize why this is important, this graph in the middle shows how the cost of change for an error early on is incredibly lower, is much lower than the cost of change later on. So if we can eliminate quality issues early on at the assembly process, again, bringing back the point of use information. If we can eliminate errors early on, right when the operator is assembling a product, we can have great change later on, because it's going to be a lot more costly to fix an error in a product that's about to be shipped than a product that's only in phase 1 or 2 of assembly. So this project is the demonstration of our assembly digital thread. The assembly digital thread project is a culmination of a lot of different things, such as machine vision model, foreign object detection, as well as bill of parts confirmation. Using the model that is the digital twin in conjunction with the camera to reference to make sure that the geometry is true and accurate. For the demonstration, I want to show and start off by saying that the programs detected 6 fasteners. The fasteners are in a certain order, which is defined by the process engineers to make sure that the fasteners are assembled in the correct order. Additionally, the correct type of fastener is listed with a certain percentage of accuracy. So if there's too little fasteners, there is an error that's shown. fastener count does not match bill of parts, missing fasteners 2 in this case, and to 3, but now we've got our 6 fasteners back. Additionally, if you add too many fasteners, it says that it's a socket head cap screw, which is accurate, but there's too many fasteners there. This is very important for companies that deal with very critical components, such as, for example, aerospace. If you're creating a turbine engine and you have one extraneous fastener, that can cause the whole engine to malfunction, fail. It can either, in the testing facility, can cause operator and tester damage. Not only the fact of losing a $500,000 machine, but additionally, fastener detection in assembly is crucial for ensuring the safety of the people that are going to be using the product. Additionally, we have our digital torque tool, which is connected to our computer via Bluetooth. But there's a QR code on this. So this QR code is for this specific tool, and it also matches where this tool is in space. So this tool has a fixed coordinate point in the center of the QR code, and no matter where I put the tool, it matches up to a coordinate in the boundary of the camera. So an operator can take their correct torque bit and add it to the assembly so that they can be prompted to go to assembly 1, and at which point this operator would go to assembly or fastener 1 and torque their values, send it to the system, and complete the assembly in the correct order. Thank you.